In the pre-dawn hours of November 8, 2025, while most of the world slept beneath darkened skies, three astronomers stood at their observation posts on a mountain somewhere in Europe. Michael Yeager, Gerald Raymond, and Enrico Prosperi were not there by accident. They were there by design, by determination, by the kind of cosmic calling that compels certain humans to spend cold nights beneath the stars, seeking answers to questions that most people never think to ask. These three observers were hunting for something extraordinary, something that had traveled across distances so vast that our minds struggled to contain them, something that had journeyed through the dark spaces between the stars for billions of years, carrying with it secrets from another stellar system, from a time before our sun had finished gathering the planets around it, from a place we may never see with our own eyes. They were watching for 3I/Atlas, the third confirmed interstellar visitor to pass through our solar neighborhood, and what they captured that morning would add another chapter to one of the most remarkable stories in the history of astronomy. Let me take you there. Let me show you what they saw. Picture this. You're standing on that mountain, your breath visible in the cold November air. The moon, nearly full, washes the landscape in silver light, making observation difficult but not impossible. To the east, just 7 to 10 degrees above the horizon, barely clearing the mountain ridges, hangs a faint smudge of light. It doesn't look like much to the untrained eye, but these astronomers knew better. They knew they were looking at a visitor from beyond, a cosmic messenger that had crossed the interstellar void. They set up their equipment with practiced efficiency. 24 exposures through a green filter, each lasting 35 seconds. 2 exposures in red, 2 in blue, each photograph capturing photons that had bounced off dust and gas particles ejected from a body that formed around another star. Think about that for a moment. Light from our sun, traveling 93 million miles in just over 8 minutes, striking particles that originated in a completely different solar system, then traveling the remaining distance to Earth to strike their camera sensors. Every pixel in their images tells a story written in light, composed in the language of physics, narrated by the cosmos itself. When they stacked those images together, combining the light from all those exposures, something magnificent emerged from the digital noise, something that made even these experienced observers pause, that made Yeager write on a community forum that they had something unusual to report. What they revealed was a complex jet structure emanating from 3I/Atlas, not just one jet, not two. At least 7 distinct jets spraying outward in multiple directions, some of them doing something that shouldn't be possible, something that defies our intuitive understanding of how comets work. Some of these jets were pointing toward the sun. Sunward jets, anti-tails, they're called in the technical literature, jets that seem to defy the very pressure that should be blowing material away. And surrounding all of this, extending outward for 5 arc minutes of sky, there was a glowing halo. 5 arc minutes might not sound impressive until you translate it into actual distance. This halo extends approximately 500,000 kilometers into space. That's roughly 1.3 times the distance from the Earth to the Moon. Imagine a glowing cloud of gas and dust, larger than the Earth-Moon system, traveling through our solar system at 68 kilometers per second with respect to the Sun. That's over 42 miles every single second. That's the span of a marathon race crossed in the time it takes you to snap your fingers. This is not a small object. This is not some insignificant speck of cosmic debris. This is a mountain-sized world, possibly as large as 15 kilometers across, though the uncertainty in that measurement is substantial. For comparison, the island of Manhattan is about 20 kilometers long. So imagine something roughly the size of Manhattan, made not of steel and glass but of ancient ice and rock, hurtling through space, leaving a luminous trail 500,000 kilometers wide, and you begin to get a sense of the scale we're dealing with. But here's where the story becomes even more fascinating. You see, 3I Atlas had just passed through Perihelion, the closest point in its trajectory to our Sun, on October 29, 2025. For several weeks before and after that date, it had been hidden behind the Sun from Earth's perspective, unobservable by ground-based telescopes. Solar conjunction, astronomers call it, when an object passes behind or in front of the Sun from our viewpoint. During that time, 3I Atlas was being scorched by solar radiation at a distance of 203 million kilometers, or 1.36 astronomical units, a distance that placed it between the orbits of Earth and Mars. At that distance, the surface of this interstellar visitor would have been heated to temperatures around 300 to 400 degrees Kelvin. That might not sound extreme compared to the surface of Venus or Mercury, but remember, this object formed in the freezing depths of another star system. It's composed primarily of ices, volatile materials that evaporate, that sublime directly from solid to gas when heated. Water ice, carbon dioxide ice, carbon monoxide ice, perhaps methane, perhaps ammonia. These materials, frozen for billions of years in the cryogenic cold of interstellar space, suddenly finding themselves bathed in the warmth of a star that is not their home sun. And so they boil. They burst forth. They create the jets that Jaeger, Riemann, and Prosperi captured in their images. The physics here is beautiful in its elegance. As the surface heats up, ices beneath begin to sublime. The gas created by this process needs somewhere to go, and it finds the path of least resistance, jetting outward from active regions on the comet's surface. These aren't uniform, steady flows. They're more like geysers, like Old Faithful in Yellowstone, but on a cosmic scale. Different regions of the surface heat up at different rates depending on their composition, their orientation to the Sun, the rotation of the nucleus. Some areas might have a thicker crust of dark organic material acting as insulation. Other areas might have exposed ice. The result is this spectacular asymmetric fountain of gas and dust, creating the jets we see. But those sunward jets, those anti-tails, those require a bit more explanation. At first glance, they seem impossible. After all, we know that the pressure from sunlight and the solar wind pushes material away from the Sun. That's why comet tails always point away from the Sun, regardless of the direction the comet is moving. So how can jets point toward it? The answer lies in geometry and the nature of dust. When dust particles are ejected from a comet, they don't all travel at the same speed, and they don't all have the same properties. Large grains move more slowly and aren't pushed as far by radiation pressure. Small grains move faster and are blown farther away. Over time, these particles spread out into a sheet, a curved surface extending around the comet's orbit. When we look at this sheet from certain angles, especially from the side, it can appear to point toward the Sun, even though each individual particle is actually moving in a trajectory that takes it away from the nucleus. It's an optical illusion, but one that's grounded in real three-dimensional geometry. The sheet of particles curves in such a way that, from our viewpoint on Earth, it appears to point sunward. However, and this is crucial, not all sunward features are mere geometry. Some comets do produce genuine jets that initially point toward the Sun. How? Through rotation. If an active region on a rotating comet happens to be pointed toward the Sun at a particular moment, the jet it produces will initially head in that direction before being bent away by solar radiation pressure. The comet's rotation causes these jets to trace out curved structures in space, sometimes creating remarkable spiral or fountain patterns. In the case of 3I Atlas, we're seeing both effects. Some of what appears to be sunward emission is probably that geometric effect, dust sheets viewed edge-on. But given the complexity of what's visible in the images, with multiple distinct jets radiating in many directions, it's likely that we're also seeing the effects of active vents scattered across a rotating nucleus, each one contributing its own stream to the overall structure. Now here's where the observations by the European team become truly significant. You see, before perihelion, While 3I Atlas was still approaching the Sun, scientists had detected something unusual. They measured what's called a non-gravitational acceleration. Let me explain what that means. When we track objects in space, we can predict their paths based on gravity alone. The Sun's gravity pulling on them, the planet's gravity tugging at them as they pass, all of it calculable with exquisite precision thanks to Newton's and Einstein's equations. But sometimes an object doesn't go exactly where pure gravity says it should. It gets a little nudge, an extra push, causing a small deviation from the predicted path. For comets, this is usually caused by the rocket effect. When gas jets shoot out from one side of a comet, they push it in the opposite direction, just like a rocket engine. It's Newton's third law playing out on a cosmic scale. Every action has an equal and opposite reaction. The comet throws mass in one direction, and conservation of momentum pushes the comet in the other direction. For 3I Atlas, this non-gravitational acceleration was measured at approximately 94 kilometers per day squared at perihelion. Now that might sound small, but over weeks and months it adds up. And here's the remarkable part. For that acceleration to be caused by normal cometary outgassing, 3I Atlas would need to have ejected a significant fraction of its total mass during its perihelion passage. Let me break down the mathematics here, because it's important and actually quite elegant. The acceleration of an object equals the force applied divided by its mass. For a rocket, that force comes from ejecting material at a certain speed. If you know the ejection speed and the desired acceleration, you can calculate how much mass must be thrown overboard. For 3I Atlas, using reasonable assumptions about the speed at which gas molecules leave the surface, about 300 meters per second, which is typical for water vapor at the temperatures we expect, the calculations suggest that the comet lost somewhere between 10 and 20% of its total mass during the month-long period around perihelion. That's an extraordinary amount. That's like if you weighed 100 kilograms and lost 10 to 20 kilograms in a month. For a comet that's potentially tens of billions of tons in mass, we're talking about losing billions of tons of material. And this is where the observations of those 7 jets, that complex structure captured by Yeager, Raman, and Prosperi, become crucial evidence. You see, if the jets were all pointing in roughly the same direction, all the mass loss would contribute to pushing the comet in one specific direction. But the images showed jets spraying in many directions. That means most of the mass being ejected doesn't contribute to the net acceleration. The pushes from different jets partially cancel each other out. Think of it like this. Imagine you're on a skateboard and you throw a basketball to your right. You'll roll to the left. Now imagine you simultaneously throw another basketball to your left. You won't move at all. The forces cancel. 3I Atlas, with its multiple jets, is doing something similar, but not perfectly balanced. Most of the jets cancel each other, but there's some net push left over that causes the measured acceleration. This means that the total mass loss must be even greater than that 10 to 20% figure, much greater. Perhaps the debris cloud we're seeing, that enormous halo extending 500,000 kilometers, represents a substantial fraction of the comet's original mass. It's as if 3I Atlas is, in a sense, evaporating before our eyes, transformed from a solid body into an expanding cloud by the intense scrutiny of our sun. Now, I need to pause here and address something that you might have heard in the news or online. There has been speculation, championed particularly by Harvard professor Avi Loeb, that 3I Atlas might not be entirely natural, that it might be technological in origin. An alien spacecraft, perhaps, or a probe sent by an extraterrestrial civilization. This is not idle speculation. Loeb is a serious scientist, and he's accumulated what he calls a list of anomalies. Let me present them fairly, because this is how science should work. We should consider all possibilities, even the extraordinary ones, as long as we maintain appropriate skepticism and demand extraordinary evidence for extraordinary claims. First anomaly. The trajectory of 3I Atlas is aligned to within 5 degrees of the ecliptic plane, the flat disk in which the planets orbit our Sun. The probability of an interstellar object randomly arriving with such an alignment is calculated to be about 0.2%. Low, but not impossibly so. Second anomaly, during July and August of 2025, 3I Atlas displayed that sunward jet, the anti-tail, which I've already discussed. Loeb argues that this is not a typical geometric effect, but represents something more unusual. Third anomaly, 3I Atlas is massive compared to the other 2 known interstellar visitors. It's about 1 million times more massive than 1I Oumuamua, the first interstellar object ever detected, and 1,000 times more massive than 2I Borisov, the second interstellar visitor. It's also moving faster than both. The probability of finding such a large, fast object before finding many smaller, slower ones is calculated to be less than 0.1%. Fourth anomaly, the timing of its arrival. 3I Atlas passed within tens of millions of kilometers of Mars, Venus, and Jupiter, and was positioned behind the Sun, unobservable from Earth, during its perihelion. The probability of such a trajectory is estimated at 0.005%. Fifth anomaly, the chemical composition of its gas plume shows much more nickel than iron, similar to industrially produced nickel alloys, and a nickel-to-cyanide ratio that's orders of magnitude larger than in any known comet. These are legitimate scientific observations, and they do present puzzles. But here's the crucial point. Unusual does not equal artificial. Nature is full of surprises. Every time we've explored a new regime in astronomy, we've found things that challenged our understanding. When pulsars were first discovered in 1967, their radio signals were so regular, so precisely timed, that they were briefly nicknamed LGM-1 for little green men, because they seemed almost too perfect to be natural. They turned out to be neutron stars, the collapsed cores of dead stars, spinning at incredible rates and beaming radio waves into space. Natural, but astonishing. When the cosmic microwave background radiation was first detected in 1965, it was so uniform, so smooth, that it seemed impossible that such perfection could arise from the chaotic process of cosmic evolution. Further observations revealed tiny fluctuations, the seeds of all future structure, but it took more sensitive instruments to see them. Natural, but mind-bending. With 3I Atlas, we're seeing something genuinely anomalous, genuinely challenging to explain with our current models of comet formation and evolution. But that's what makes it scientifically valuable. It's telling us that our models are incomplete. It's teaching us that planetary systems around other stars can produce objects with characteristics we haven't seen before. Consider the carbon dioxide abundance. Observations from the James Webb Space Telescope showed that 3I Atlas has one of the highest carbon dioxide to water ratios ever measured in a comet, about 8:1. Most solar system comets follow a predictable trend where this ratio changes with distance from the Sun. 3I Atlas breaks that trend spectacularly. Why? One possibility is that it formed very close to the carbon dioxide frost line in its parent star's protoplanetary disk, the distance from the star where carbon dioxide ice can stably exist. Different formation locations create different compositions. Another possibility is that it has an unusually thick crust of organic material insulating water ice beneath, limiting how much water can escape compared to carbon dioxide, which sublimes at lower temperatures. These aren't failings of natural explanations. These are opportunities for discovery. Each anomaly is a thread that, when pulled, might unravel a whole new understanding of how planetary systems form, how comets evolve, how material migrates through galaxies. The jet structure observed by the European team adds another data point to this investigation. 7 distinct jets, multiple directions, complex morphology that changes over time. Is this the signature of a natural comet with a heterogeneous surface, pockets of different ices exposed as the surface erodes? Or is it, as Loeb suggests, potentially evidence of multiple thrust vents on a spacecraft? The honest scientific answer is we need more data, and that's okay. That's how science works. We don't have to jump to conclusions. We can be patient, rigorous, methodical. What we do know for certain is that 3I Atlas is active, spectacularly so, as evidenced by the observations from November 8th. It's shedding material at an extraordinary rate. It's creating structures in its coma that are visible to ground-based telescopes, despite the challenging observing conditions of bright moonlight and low altitude, and it's continuing on its journey. After passing Perihelion on October 29th, after creating this magnificent display for the European observers, 3I Atlas is now heading outward from the inner solar system. On November 3rd, it passed about 97 million kilometers from Venus. In mid-December, specifically December 19, 2025, it will pass approximately 269 million kilometers from Earth. That's nearly twice the Earth-Sun distance. It will never pose any threat to our planet. Next year, on March 16, 2026, it will pass about 54 million kilometers from Jupiter. That's close enough that NASA's Juno spacecraft, currently in orbit around the giant planet, might be able to detect it with its imaging instruments and radio receivers. Imagine that. A spacecraft designed to study Jupiter suddenly having the opportunity to observe an interstellar visitor. Such serendipitous moments are rare in astronomy, and scientists are already planning how to take advantage of it. Then, after that Jupiter encounter, 3I Atlas will continue outward, past the orbit of Saturn, past Uranus and Neptune, gradually fading from view as it recedes and as solar heating diminishes, shutting down the outgassing that makes it visible. Eventually, probably sometime in 2027 or 2028, it will become too faint for even our largest telescopes to track. And then it will be alone again, sailing through the dark between the stars, carrying with it whatever secrets we failed to extract, heading toward some distant future encounter with another star system perhaps millions of years from now. But it will leave behind something invaluable: data. Images like those captured by Jaeger, Riemann, and Prosperi. Spectra showing the fingerprints of molecules in its coma, measurements of its trajectory, its brightness, its evolution over time. All of this will be archived, analyzed, reanalyzed, forming the basis for papers and dissertations and debates for years to come. And that brings me to perhaps the most important point I want to make. The observations of November 8th weren't made by a billion-dollar space telescope. They weren't made by professionals working at a major observatory. They were made by dedicated amateur astronomers, people who pursue this passion because they love it, because they're drawn to it, because they understand that we live in a universe of wonders and that we have the privilege, the responsibility even, to study those wonders. Michael Jaeger is an Austrian astrophotographer who has discovered numerous comets and made significant contributions to cometary science. Gerald Riemann is also from Austria, known for his exceptional images of comets and nebulae. Enrico Prosperi is an Italian amateur astronomer and astrophotographer who has contributed to numerous discoveries and observations. These are not household names, but they should be celebrated nonetheless. They represent a tradition in astronomy that stretches back centuries, to the era when all astronomers were amateurs in the sense that they weren't paid professionals. They were simply people fascinated by the sky. William Herschel, who discovered Uranus, was a musician and composer who built telescopes as a hobby. Carolyn Herschel, his sister, who discovered several comets and compiled star catalogs, started as an amateur. Many of the asteroids and comets in our solar system were discovered by dedicated amateur observers. Today, we live in an era where professional astronomy is dominated by large collaborations, space missions costing billions, telescopes the size of buildings. But there's still room, still need, for individual observers with modest equipment and extraordinary dedication. The sky is vast. There are more things to observe than all the professionals in the world could ever track. And sometimes, as with the November 8th observations of 3I Atlas, amateurs see things first, or see them better, or see them when no one else is looking. This is one of the beautiful aspects of astronomy. The universe doesn't care about your credentials. It doesn't check your PhD before revealing its secrets. It simply asks that you look carefully and persistently with whatever tools you have available. And what tools they have today. Modern cameras, even relatively affordable ones designed for amateur use, can detect light levels that would have been impossible to see just a few decades ago. Computer software can stack dozens of images together, pulling faint signals out of noise. The Internet allows instant sharing of discoveries and coordination of global observing campaigns. We're living through a golden age of amateur astronomy, a time when citizen scientists can make genuine contributions to humanity's understanding of the cosmos. The story of 3I Atlas and its jet structure is really multiple stories woven together. It's a story about the interstellar medium, about the spaces between stars, which turn out to be not empty but filled with wandering objects, ejected from their birth systems by gravitational encounters, drifting through the galaxy for billions of years. We've now confirmed 3 such objects passing through our neighborhood, and statistical analyses suggest that there should be thousands, perhaps millions, within the boundary of our solar system at any given time. We just can't see most of them because they're too small or too far away, or moving in directions that don't bring them close enough for detection. It's a story about planetary formation, about how stars create families of worlds, and how those families are often larger and more chaotic than we once thought. For every planet that settles into a stable orbit, dozens or hundreds of planetary building blocks are flung outward, exiled into interstellar space. These objects carry chemical fingerprints of their formation conditions, messages written in molecular abundances about the temperature and composition of the regions where they coalesced from the protoplanetary disk. It's a story about technological capability, both present and potential. Our current technology, while impressive, is barely adequate to study objects like 3I Atlas. We can see them, measure their basic properties, take spectra, track their paths, but we can't get detailed close-up views. We can't analyze their composition directly. We can't land on them or even send a probe for a flyby with current technology, not on the timescales required. By the time we detect them, plan a mission, build and launch a spacecraft, they're already gone. But imagine, just for a moment, what future technology might enable. Imagine a network of telescopes and sensors positioned throughout the solar system, providing constant surveillance of the sky from multiple vantage points. Imagine rapid response spacecraft already built and waiting, ready to launch on short notice when something interesting is detected. Imagine artificial intelligence systems capable of analyzing data in real time, spotting anomalies, coordinating observations across multiple platforms. Such capabilities are not science fiction. They're engineering challenges, and if we choose to invest in them, if we decide that understanding our cosmic neighborhood is worth the resources, we could build such systems within a few decades. And it's a story about ourselves, about humanity's place in the universe. We are, as far as we know, the only species in the galaxy that builds telescopes, that studies the sky, that asks questions about our cosmic origins and our cosmic destiny. That's a profound privilege and a profound responsibility. Every time an object like 3I Atlas passes through our solar system, it's an opportunity to learn, yes, but also an opportunity to be reminded of the scale and complexity of the universe we inhabit. It's easy to become absorbed in our daily concerns, to forget that we're living on a small planet orbiting an average star in the suburbs of a spiral galaxy containing hundreds of billions of stars, in a universe that may contain hundreds of billions of galaxies. Objects like 3I Atlas, visitors from other star systems, make that cosmic context undeniable. They carry with them the implication that there are other solar systems out there, other worlds, other histories of planet formation and evolution. And if there are billions of planetary systems in our galaxy alone, the question becomes not whether some of them host life, but how many do, and how we might someday make contact. The jets emanating from 3I Atlas, captured so beautifully by the European team, are made of simple molecules: water, carbon dioxide, carbon monoxide, cyanide, traces of nickel, and other elements. None of these are alive. None of them are thinking. But they're the building blocks from which life can emerge, given the right conditions, given enough time. Earth's oceans, the water that makes up most of your body, may have been delivered in part by comets crashing into our young planet billions of years ago. The organic molecules found in comets, the carbon compounds that form when simpler molecules are irradiated and chemically transformed, are the precursors to the amino acids and nucleic acids that form the basis of all life on Earth. When you look at an image of 3I Atlas with its glowing coma and multiple jets, you're not just looking at a distant object. You're looking at a piece of cosmic history, a fragment of the process that created everything you see around you, everything you are. The observation on November 8, 2025 will become a footnote in the larger story of 3I Atlas. It will appear in papers and databases, in catalogs of cometary observations, in the archives maintained by organizations like the International Astronomical Union and the Minor Planet Center. Future students studying for astronomy exams will memorize the basic facts. Third interstellar object discovered July 1, 2025, perihelion October 29th, complex jet structure observed post-perihelion by European team. But the real significance goes deeper. Every observation, every measurement, every image contributes to a vast tapestry of knowledge that we're weaving together generation after generation. We're mapping the cosmos, understanding its contents and its laws, its history, and perhaps even glimpsing its future. And we're doing this together. Not just scientists in laboratories and observatories, but dedicated amateurs like Jaeger, Raymond, and Prosperi, citizen scientists analyzing data from space missions through online platforms, students doing undergraduate research projects, retirees who've taken up astronomy as a passion, engineers and teachers and artists and programmers, all contributing in their own ways. The universe is vast enough that there is room for everyone. The questions are deep enough that we need all the help we can get. The wonder is profound enough that it should be shared as widely as possible. As I bring this narration to a close, I want you to take a moment to appreciate what we've witnessed together. An object from another star system, traveling for billions of years through the cold and dark, happened to pass through our neighborhood. A few observant humans using sensitive cameras and careful technique captured its portrait at a crucial moment in its journey. The light from those jets, carrying information about chemistry and physics and dynamics, crossed millions of kilometers of space to reach their sensors. And now, through the miracle of modern communication and the generosity of those observers sharing their data, you know about it. You've connected with this cosmic visitor in a small but real way. That's extraordinary. That's worth celebrating, because in the end, astronomy isn't just about collecting facts and solving equations. It's about expanding our perspective, enlarging our sense of what's possible, connecting ourselves to the larger universe of which we're a part. 3I Atlas, with its 7 jets radiating in multiple directions, its glowing halo extending across vast distances, its complex and still not fully understood behavior, reminds us that the universe is stranger and more wonderful than we can easily imagine. It challenges our theories. It raises new questions. It invites us to look closer, think harder, wonder more deeply, and that invitation, that call to curiosity and investigation, is one of humanity's greatest gifts to itself. We don't just survive on this planet. We observe, we question, We seek understanding. The jets of 3I Atlas, captured by 3 dedicated observers on a mountaintop in Europe, are more than just features in a comet's coma. They're invitations to explore, invitations to discover, invitations to continue the grand human project of understanding our cosmos. And somewhere out there, billions of kilometers away now, and receding every second, 3I Atlas continues its journey, carrying its secrets with it, heading back toward the stellar realm from which it came. It doesn't know we're watching. It doesn't care about our theories or our debates. It simply is, following the laws of physics, responding to the warmth of our sun, gradually returning to the cold. But we remember, we record, we study, we learn. And that, ultimately, is what makes us human. Not just our ability to observe the universe, but our insistence on trying to understand it. Our refusal to accept mystery when explanation might be within reach. Our drive to know, even when knowing is difficult, even when the answers challenge our preconceptions. The European team's observations of November 8th have added their verse to the long poem of human discovery. And that poem is still being written. Every night, somewhere on Earth, someone is looking up. Every day, new data arrives from our spacecraft scattered through the solar system. Every year brings new instruments, new techniques, new opportunities. The cosmic visitors will keep coming. The universe will keep surprising us. And if we're wise, we'll keep watching, keep wondering, keep that flame of curiosity burning bright against the dark. Thank you for joining me on this journey. Thank you for caring about a comet with a complex jet structure, about 3 observers on a mountain, about the ancient dance of matter and light that creates the phenomena we study. Keep looking up. Keep asking questions. Keep being amazed, because the universe is amazing, and so is your capacity to understand it.